We are in Chapter 3 in Section 2, and we are looking at the bottom of page 146 at the range rule of thumb. So we have talked about range earlier in this section, but then it's really nice when we can find some fast ways to do stuff where the range rule of thumb can be used to approximate standard deviation. What? So you need to grab your formula card, and as soon as you look at Chapter 3, you need to notice that it is there. They list the range rule of thumb. And again, on the first test, you're not using the formula card, but we are getting this formula card ready for when we do use it on one of our tests. And so the range rule of thumb, as you see here, has standard deviation is about equal to the range cut into 4 parts. And that's what it says here, a rough, nice word, a rough estimate of the standard deviation. Because at this point, you're probably thinking, man, that thing takes forever to calculate. Even with a shortcut, it can take forever. But it works, and it may be tedious, but it's definitely doable. But then, let's say you're in the middle of the test, you got to do this the really long way, and then all of a sudden you're thinking, I'd love to double check this, because that's a really good testing strategy. Then what you could do is just do a quick range divided by 4 and see if the answer you got going the long way and the answer you got with this rough estimate are very similar. They won't match, but at least you can have an idea of reasonableness. So I'm at the top of page 147. See a whole lot of stuff going on, and the whole lot of stuff going on is actually for this next part. And so all I want to do is just read a little bit right here that says there was another one that we did, and if we use the range rule of thumb, in this case it underestimates, and so it can under or overestimate. However, it's still in the ballpark. The range rule of thumb is only an, huge word, approximation, and should be used when the distribution of data values is unimodal and roughly symmetric. So remember, I'm asking you to have like a list of vocabulary, maybe a glossary of your own vocabulary, or index cards. I really like index cards because it separates out the information and it allows you to memorize pieces and parts at a time and not feel overwhelmed. But however you're doing it, make sure on this range rule of thumb, you do note that it works best when you have a distribution of your data values that is unimodal and roughly symmetric. The range rule of thumb can be used to estimate the largest and the smallest. The smallest is going to be approximately 2 standard deviations below, and the largest about 2 standard deviations above. For many data sets, most all of the data values are going to fall within 2 standard deviations of the mean. That's going to lead us into this next part. I'm only at 3 minutes, so I'm going to keep going. Better approximations can be obtained by using Chebyshev's theorem and the empirical rule. So the empirical rule is going to show up on another video, but we are now going to go from range rule of thumb, that concept, and then to this one, Chebyshev's. His theorem. You need to memorize these 2 numbers, 75% and 88.89%. You need to see my notes. You need to memorize these. This first one, well, let me just read and not jump the gun here. As stated previously, the variance and standard deviation of a variable can be used to determine the spread or the dispersion of a variable. That is, the larger the variance or the standard deviation, the more that the data values are dispersed. Jumping down here, Chebyshev's theorem developed, can't see where my finger is. Chebyshev's theorem developed by a Russian mathematician, Chebyshev. He lived in the 1800s, and I'm just hoping somebody remembers something that I have said or done in a positive manner this far out, a couple of 100 years out, whenever I'm gone. Specifies the proportions of a spread in terms of standard deviation. Here is Chebyshev's theorem. Chebyshev's theorem is as listed here. You do not need to know the theorem for our class. Here's what you need to know for our class. Up here I mentioned the 75 and 88.89. The theorem states that at least 3/4, or 75%, of the data values will fall within 2 standard deviations. That's what you need to know, is that 75% of the data values are going to fall within 2 standard deviations of the mean of the data set. And we can find, there's a lot more that we can do with this. In our class, we're just scratching the surface. You need to know that 2 standard deviations represent 75% of the data values. But there's another amount, 88.89. You can probably see in my writing there, it represents 3 standard deviations. There's more of this on the next page, but before we go over there, I want to show you a quick drawing. And so looking at our quick drawing on our standard deviations. So 1 standard deviation, 2 standard deviations, and 3 standard deviations. So 1 standard deviation is not represented here. 2 standard deviations is. 2 standard deviations will represent 75% of the data values. 3 standard deviations, let me see if I can find my green pen pretty fast. And nope. So 3 standard deviations will represent 88.89% of the data values. And moving on to page 149, actually 148, it says, furthermore, the theorem states that, and this is the 88 or 8/9 of the data will be fall within 3 standard deviations of the mean. Going straight down to here. I'm jumping all of this. We are not working through the 1 minus 1 over k squared. Again, we are just talking about 2 standard deviations is 75%, 3 standard deviations is 88 and 89/100%. Here's where it's stated, but I want you to make sure that you write in a couple of other words. In summary, that's what we're doing. Chebyshev's theorem, and this goes for any shape. That's the cool thing about his. It doesn't have to be normally distributed. It can be any shape. 3/4, 75%, 2 standard deviations. 89 or 88.88%, 3 standard. This theorem, sorry, I'm jumping around and not being very clear, but this theorem can be applied to any distribution regardless of its shape. I think I've said everything I wanted to say, and I've skipped the stuff I want to skip, but what I do want to look at is this example. And when you get to this example, I would follow through with me, and then I would go back by yourself, and I would cover up the problem itself, and then do it by yourself. So let's start with the by yourself part, kind of. The mean price of houses in a certain neighborhood is this. That's the mean. It's 50,000. So I'm thinking, okay, and on a normal curve or on what we're talking about, it's going to go in the middle. The standard deviation is 10,000. Find the price range for at least 75% of which at least 75% of the houses will sell. Mean is 50. Standard deviation is 10. They're asking for 75%. So I'm going to cover all of this stuff up. I'm going to draw, and I'm just going to pretend normal, although it doesn't have to be. That's just what my brain sees. So the mean is at 50,000. It says each standard deviation is worth 10,000. So I'm going to play with this for a second. If each standard deviation is worth 10,000, if I'm going up, then this is 60,000. Another 1,000 is 70,000, or sorry, another 10,000. And then another 10,000 puts us at 80,000. If I'm going backwards, going down on my standard deviations, when I subtract, I get 40,000 and 30,000 and 20,000. So make sure your brain's seeing this is going to be our mean and how to calculate the standard deviations going up and down. The question said, right there, for at least 75% of the houses. So 75% has to cue in your brain that we're talking Chebyshev, and 75 for Chebyshev means 2 standard deviations, which also means 2 standard deviations. And so what's the range going to be? From 30,000 to 70,000. Very last sentence, hence, at least 75% of all the homes sold in the area will have a price range from $30,000 to $70,000.